Thanks everyone. Welcome to the Barnett Award session. The Barnett Award was established in memory of the environmental statistician, Professor Vic Barnett. It's awarded annually to encourage and promote the recognition of outstanding contributions to the field of environmental statistics. The Barnett Award winner also delivers the Barnett Lecture at the RSS Annual Conference, where we are now. In 2025, the award goes to Professor Claire Miller of the University of Glasgow. Claire's leadership in applying statistical approaches to real-world environmental challenges has produced monitoring and research methodology used in both the UK and indeed worldwide. Claire has made exceptional contributions to environmental statistics, leading work in water quality measuring, monitoring and forecasting in particular. Claire was president of the International Environmetrics Society until Sunday, and the TIE's website is currently down in mourning. Just as a reminder, you can submit questions for Claire through the app at any time through the talk, and if there's time, we'll also invite questions from the floor. There will be somebody, I think, roving around with a microphone in a yellow t-shirt. So it now gives me great pleasure to invite Claire to deliver the 2025 Barnett Lecture. Thank you, Claire.
Many thanks, Mark. Very much appreciated. I feel very honoured to be giving this lecture here today. And so what I would like to do is to take you through some previous projects, but also questions that we've been interested in and find exciting. I'd like to introduce some of the teams and collaborators that are really pivotal to all of that work. I'll then go into talking about environmental data a bit more broadly. I'll introduce some of the approaches we are developing in data fusion and integration. And then I'll highlight some opportunities that you might be interested to get involved with. Finally, we'll look to the future. So some ideas that we are looking at for the future, but also for environmental statistics in general. So, what is the status of lake water quality for 1,000 large lakes globally? This was the focus of our Global Lakes project. Global Lakes was funded by the Natural Environment Research Council. And here we looked at data from MERIS. So MERIS was a satellite on the European Space Agency ENVISAT platform. MERIS looked at colour reflectance from the lakes, and it gave us information spatially at 300-metre resolution and passed over about once every 2 to 3 days in terms of globally. So from the colour reflectance, our colleagues at the University of Stirling and at Plymouth Marine Laboratory produced a chlorophyll product for us to work with. And we looked at chlorophyll in these 1,000 lakes, all denoted here by these colour dots. So we were interested in the temporal patterns for chlorophyll, but more importantly, we were interested in where we saw common patterns or where we saw temporal coherence. Lakes are regarded as sentinels of change, and so we were interested in identifying those common patterns, the drivers, and what they might tell us about environmental change. Now, of course, lakes are not in isolation. They play a key part in connectedness within ecosystems, and that's what we were interested in for our Hydroscape project. So in Hydroscape, this was working within Great Britain, and we were looking at how ecosystem responses change depending on connectivity, with freshwater connectivity being one level, and also how they change depending on land use catchment stressors. So we were interested in the species distributions, the species abundance, and what effect the connectivity and stressors had. Now, of course, rivers and groundwater play a key part of that ecosystem as well. And we've worked with both the environment agencies and also with industries such as Shell to look at how does river and groundwater quality change over space and over time. And of course, importantly, where and when should we monitor? But those are all very classical questions in environmental statistics that people have been looking at for a long time. And one of the projects that we're working on now is really taking us to the challenges that we see today. So in MOT for rivers, we're interested in mixtures. We now have emerging potential contaminants and pollutants in our rivers and water bodies. And it's not about just the individual effects of these particular determinants, but what might the interactions be, what might the mixtures be. So in MOT for rivers, we're linking together these different data sets across Scotland, England, and Wales. We have water quality data, over 1.6 million observations, linking to biology, invertebrates, diatoms, and macrophytes, and also looking to build in catchment information, looking at combinations, interactions with hydrology, with climate, and with surrounding land use. So that takes me to our collaborators. All of the projects that I've mentioned have involved a large number of people. And this just shows you some of the collaborators that are involved in the projects that I'm talking about today. So we've worked with many different universities. We've worked with different organisations across the environmental sector, James Hutton Institute, CEH, the environment agencies. And in the work that we've been doing, we've been the main team in terms of statistics or data analytics. So in the different universities here, we've been working across departments of environmental science, geography, environmental engineering, and remote sensing, all to look at the types of questions and projects that I've introduced so far. Now, that was external collaborators, but I wanted to take a minute to recognise the very large team that I work with at Glasgow and also our group at Glasgow. So the people listed here, always a dangerous thing to do. I've probably missed someone, but the people listed here are all the people that are involved in direct collaborations that I'm working on just now. In the far left here, all these people involved in the projects I'm talking about today, some previous colleagues and students in the middle. But even though this is a reasonably large list, it's still just a subset of the number of people that we have working in similar areas within Glasgow. So I'm part of the Statistics and Data Analytics group at the University of Glasgow. Within that group, we've got about 35 full-time academics, about 10 postdocs, and about 40 PhD students. And a large majority of them are working in areas related to environment, ecological sciences, and sustainability. The word cloud in the bottom right here is an attempt to summarise some of that. So not just my work, but the work right across the group at Glasgow. Many different things being picked out, but the one thing that screams out at you is data. Data is driving a lot of what we're doing in terms of the work, in terms of these projects. And the reason for that is that we're interested in these global environmental challenges that I've started to outline today. So we're interested in the data that we can use in order to investigate and understand those challenges. And of course, we're interested in what we need to develop in statistics and data analytics in order to aid that understanding. So these are some of the potential environmental data sources that are available now. Sources are continually evolving and expanding. It's a very fast-paced area. Traditionally, in environmental processes, you would go out and take a manual sample for the environmental process that you were interested in. That's still available. We still have in situ sampling, but it's moving more and more to looking at automatic sensors, buoys, sondes within the water. I've talked about satellite data already. It's continually expanding. We have optical, we have radar, we have LiDAR, lots of different possibilities. Additionally, in remote sensing, drones, aircraft imagery. But now we have different types of data that can be useful as well. Data are all around us, whether it's social media data, citizen science data, and of very different forms and types. Photographs, images, public opinion posts, it could be videos, it could be audio acoustics. So there's lots of potential out there in terms of environmental data. But if you take water quality as just one example, there's no one source of data that can give us a complete picture. And so the power here is really, how can we think about combining different data sources together? But these data sources themselves all vary. So some will be at different spatial or temporal resolutions, different levels of uncertainty, and you may or may not regard them as being representative for what you're interested in. So that brings me to fusing and integrating data streams. So a whole choice of potential data sources. If we can sensibly fuse or integrate those data streams, then it can enable estimation or prediction with greater global coverage, with higher spatial resolution, higher temporal frequencies, and hopefully with reduced uncertainty. But we want to go further than that. It's not just about prediction. There's lots of tools for prediction. It's about how can we unlock insights? How can we understand about interactions within environmental pressures? And if we can do all of that, then it would give us a greater understanding about our environment, but also to allow us to inform planning for healthy, sustainable ecosystems of the future. So, the thing most of us are working on and interested in is those statistics or data analytics challenges. So what are those challenges when it comes to combining complex and diverse data streams? Well, I've already mentioned that the data could have different spatial or temporal support. So we might have data that come from a point source, or we might have data where we have a high spatial coverage. This can give us a large amount of data when we combine different sources. But within the environment, we're still having issues of missing data or sparse data. For example, if we take automatic sensors, a sensor could malfunction. It could be covered by leaves, for example, that block the signals. An animal could kick a sensor, knock it off. Satellites can be affected by cloud cover. They can be affected by land masking. They only pass over at different temporal resolutions. So we need to be able to account for these things and combine them within our statistical approaches. This means that we've got variety in terms of the quality of the data streams that we're working with. We need to be able to account for varying levels of uncertainty and also varying levels of spatial representativeness. Now, with that uncertainty and the complexity, also with processes being observed across, for example, networks, it brings us to complex spatiotemporal covariance structures that we need to be able to account for. And the first three bullets there, still thinking actually quite traditionally in the forms of our data. As we move to more non-traditional forms of data, we've got variety in form and type. We've got structured and unstructured data, qualitative and quantitative. How do we combine all of that? But then how do we give people answers in real time with as accurate and narrow uncertainty intervals as possible? So lots of ongoing challenges there. So I thought I would motivate this area of data fusion by talking about an example that we worked on a few years ago. And so this is an example from Lake Balaton in Hungary. And we looked at the spatiotemporal patterns using in situ data and satellite data. So in this specific example, we had 9 locations from within the lake for Lake Balaton. And you can see those 9 locations indicated by a dot on the coloured surface of the lake. And then we also had satellite data. So I mentioned MERIS earlier. So we had information from MERIS, and that was here for 7,616 pixels, which is given a coloured surface across the lake. Our main indicator here, we were interested in chlorophyll, that I mentioned earlier as well. Chlorophyll is an indicator of water quality. It gives us an indication of the amount of phytoplankton biomass in the water. And as the levels of chlorophyll increase, that might indicate that we've got poorer water quality. So here we were interested in how do we fuse these two products. How can the in situ and the satellite data be fused to combine the spatial and temporal information from the two sources in order to give us a high-resolution image where we can predict anywhere across the lake in space and time, and also have uncertainty information. So on the left there, you've got the same picture that we had in the previous slide. And if you look in round about, not sure you can see the green dot very well, round about 5 and 6 in the middle there. So the colour on the point is the measurement from the in situ data. The satellite is underneath. So you can see the discrepancy there between the in situ and the satellite. And this is a matched time point. On the right-hand side, we have information over time, and that's from location 1, which is right down in the far corner of the lake. So over on the right here, we have our in situ data in the black with the points, the satellite at a matched pixel this time in the red. And again, you can see the difference in the variability that we have between the two. So with this, I'm going to give you an example of some of the approaches that we've been working on and developing. First of all, I'll say a little bit about non-parametric downscaling to extend this lake's example. And Craig and Zhao-Yan have been working on this. I'll then move application area a little bit and tell you a little bit about Pietro and Weiyu's work looking at wind speed and soil moisture. So how can we fuse together these two data sources? Picture in the bottom left and the top right, these are the pictures that I've already shown you. The one in the bottom right here is just to give you an indication of the building blocks, if you like, for the approach that we took. For a long time now in the group at Glasgow, we've done a lot of work on smoothing. And as we went through some of the projects that I mentioned earlier, we've developed smoothing, functional data analysis, functional clustering approaches. But here we used smoothing as the building blocks to this non-parametric statistical downscaling approach. And what this is allowing us to do is to match our in situ and our satellite data using curves. So for those that don't like equations, I apologize, I don't have many, just a few slides. But here, just to give you an indication, the Y here is our in situ. So the Y's are in situ. We have a smooth curve for our in situ data, and that's built up from basis coefficients and basis functions, our C and our phi. We also have a smooth curve for our satellite data in X, and that's a matched pixel initially. And again, that smooth curve coming from D and from psi. And what we do is we essentially regress those curves. So we have spatially varying coefficients in order to come up with our basis coefficients C. So we have spatially varying coefficients in alpha and beta. And then on top of all of that, we're working in a Bayesian inference framework, and so we have our prior distributions here for alpha and for beta that have underlying spatial processes. And so fitting that allowed us to come up with our high-resolution image and patterns over time for chlorophyll within Lake Balaton. The image here is just showing you one snapshot in space, and so just at one particular time point is the high-resolution image up on the top there, where we can predict across the lake after we've fused the in situ and the satellite. And then the bottom image there, we've got the standard errors giving us the uncertainty for each of those predictions. So that was just to motivate some of what we're working with in terms of data fusion. And I'll just take you through some of the other developments that we've been looking at. So Zhao Yan looked to extend the work in Wilkie et al., thinking specifically about moving from chlorophyll from the satellite to reflectance. So I mentioned at the beginning that MERIS looks at colour reflectance from the water. And then our colleagues in Stirling and Plymouth Marine Laboratory produced that level 3 chlorophyll product for us through algorithm. But if we could go back a stage, if we could look directly at the reflectance from the satellite data instead, then this avoids us having to do the final algorithm stage, but it also might provide additional information. So Zhao Yan worked on this, and as part of this, then developed further this non-parametric statistical downscaling approach. Of course, as we scale things up, as we look at reflectance, we're looking across the whole wavelength spectra instead of just at specific points. And so we have higher dimensions. And so just in this example here, Zhao Yan has introduced Gaussian predictive processes as one way in order to help to speed up in the covariance structure for alpha and beta in those priors. So estimating that at a lower dimensional spatial process in order to help with computation. Additionally, as part of this, he also looked at then how this scales up, because now we're looking across space, time, and wavelength, and so we need a multivariate formulation of the model. I wanted to change direction slightly just to tell you about some of the other work we've been doing in data fusion, because this is a very hot area just now. Many people are working in this area, and there are, of course, different approaches that you can take. Our approaches have very much been driven by what we see in the data and very much motivated by different applications of interest. So on the left there, first of all, Pietro has developed warped multifidelity Gaussian processes. And this was motivated by wind speed. And so for the wind speed example, we had data from the Lombardy region of Italy, which is in northern Italy. The data themselves, in terms of the in situ data, came from the Environment Agency there, ARPA Lombardia. And in this case, Pietro was interested in looking at fusion between that in situ data source that was working with hourly measurements and about 120 ground locations, and fusing that with the ERA5 reanalysis product. So that's a product from the European Centre for Medium-Range Weather Forecasting. It's a combination of a modelled and a satellite product that pulls in satellite and other in situ data. So Pietro was interested as to how he could develop Gaussian processes in order to do this data fusion. WEU's example was a bit different, soil moisture. WEU is looking at soil moisture from the Elliott water catchment. The Elliott water is in Arbroath, which is on the east coast of Scotland. And there we have far fewer sensors. So we have around 20 in situ sensors. And WEU has been looking at approaches to fuse that information with information from Copernicus. And Copernicus satellite here is at 1 kilometre resolution. So this is just to give you an overview of some of the approaches. In both cases here, the main aim is to come up with the high resolution predictions, combining the data sources and accounting for the uncertainty. Warped multifidelity and Gaussian processes up the top, and we use spatiotemporal regression down the bottom. And in these specific cases, we're often working with the fact that the in situ is the more accurate product. So again here, we're thinking about the in situ data in Y, the in situ data, a high fidelity data source here, more accurate data source, but not recorded at as many spatial locations. And Pietro's looked at using Gaussian processes in order to link together the in situ and the ERA5 product. And he's currently working on extensions of that for a spatiotemporal model. So this specific model here is for a matched point in space, but developments at the moment are taking this out to spatiotemporal by incorporating the Vecchia approximation as well. And a key thing here was the warping that was built in order to take account of the skewed distribution that we have for wind speed. WEU's model is expanding things a bit more because she's specifically interested in additional covariates. So not just fusing together the soil moisture in terms of in situ and satellite, but actually can we build in additional information? Can we build in information from rainfall that we've also got in sensors, soil temperature in sensors as well, and from more global elevation products? This specific example, a bit of a different route, again, related, but this time a Bayesian hierarchical model, where we're integrating the in situ and the satellite data for soil moisture, or volumetric water content, through a common latent spatiotemporal Gaussian field and fitted through INLA. So that was a few examples in data fusion, and mainly thinking about linking together the same variable. But of course, we want to try and build in different data types as well, and think about how we might integrate them in order to understand our ecosystems. So the first project here, MOT for Rivers, I mentioned right at the beginning. I won't say any more about that today. I'll just mention that Ian has a poster tomorrow, so an advert for his poster tomorrow, number 58. Ian is working in an area related to MOT for Rivers, thinking about multivariate responses for metals within river catchments, and this is with the Environment Agency. The one I want to focus on to give you my final research example is one of our more recent projects called Gallant. So this is a bit different from the other things I've been talking about today, but is a really good example of where we have very diverse data types and where a lot of this work is going in terms of moving towards a systems approach. So Gallant is Glasgow as a living lab accelerating novel transformation. It is a city-university partnership with Glasgow City Council, and again, it's funded by the Natural Environment Research Council. The project's been running from 2022 and it runs through to 2027. So this is the makeup and what we're trying to do within Gallant. We're trying to use cross-disciplinary expertise to drive systemic transformation. Now, actually, it's more than that. It's actually transdisciplinary in terms of the project. Because while we're working across many different disciplines, we're also working very closely with policy colleagues, but also with communities, so direct residents within Glasgow. We want to look at this transformation in terms of economic development so that it's responsibly considered through ecological and social lenses. So what does that mean? Well, we have 3 overarching work streams, and if I take work stream 1, systems transformation initially, they are working under a framework called donut economics. And the idea behind donut economics is that we're working to be ecologically safe and socially just. And what that means is that we want everyone in society to have what they need. We want society to be able to thrive, but we want to do that within our planetary boundaries, so while we're protecting the planet at the same time. So workstream 1 keeps us under that systems framework. Workstream 2 is our community collaboration group. They work in Govan, in Anderston, and in the south side of Glasgow, directly bringing communities into this research. And then you're probably not surprised that we're in workstream 3. So I lead the data and data analytics workstream for Gallant, and I'll say a little bit more about that later. Underlying our work streams, we have 5 work packages. We have flooding, biodiversity, vacant and derelict land, active travel, and clean energy at the community scale. So this is what we're trying to do. We're trying to learn about Glasgow's living space, how it's changing, what effect interventions might have on the future environment, economy, etc. As I mentioned, it's a very large project. It's entirely based at Glasgow in terms of the research. So there's more than 70 of us at Glasgow working on this, but with many external partners and the City Council being a key partner. The overarching idea with Gallant is, can we come up with a prototype that can then be used in other cities as well? So just to give you an indication of some of the data we're working with and what we're doing in workstream 3, the data here are quite different. We have data from our community participants, we have photos, we have interview transcripts, we have more traditional data, deprivation indices, And we've been looking at social media data. Within the different work packages and work streams, they have sensor data, they have video, they have acoustics, and so on. So many different diverse data streams for us to try and investigate and understand about patterns of sustainability. So within our team, Luigi has been working on various AI pipelines to move in the first instance from photos or social media posts through to image descriptions and understanding what people are posting about, what people are interested in. Part of this is thinking about sentiment. Do people feel positively or negatively about things? But also about event detection. And just to give you one example of that, this is an example of Luigi's work looking at Flickr. So Luigi did a lot of setup, processing, streaming down from the API to get Flickr posts related to biodiversity within Scotland. From 2019 up to 2024, there were 30,000 posts here in all. And this is just showing you one specific example. So in one specific example post, we have an image from Flickr. Then deep learning used to extract description of that image, give sentiment to the image, and here we can see we've got negative sentiment. Trees falling down based on the storm, fallen tree. So an indication that we might be able to point towards some event detection. But what we're interested in is how can we link that all together? How can we link it together with other data sources, with what we find in the community, and then how can we use it moving forward? So that brings me to opportunities. If you would like to know more about what we're doing in Gallant and Workstream 3 in particular, then that's the QR codes up the top. The QR code down the bottom if you are interested to come and work with us. So we do have a vacancy at the moment within our team. This would be to do the nature of the work I've been talking about. So cross-cutting data analytics and AI pipelines across our Gallant work packages and work streams to explore these patterns in sustainability from multiple data sources. Deadline's 15th of September. So if you or anyone you know, please point them towards this. Very happy to talk about it later. I just wanted to take a moment along with that, though, to point out other opportunities within environmental statistics. Many of you will know that the RSS has an environmental statistics section and a climate change and net zero task force, and I'm a member of both of these. As you'll know, there's various streams and talks this week directly in those areas that you can follow. And Mark mentioned at the beginning that just 2 days ago, I finished being the president for the International Environmetrics Society. Now, TIES is very much grounded in everything I've been talking about today. Statistics and data analytics, quantitative analysis for the environment, but also with a key aim of linking together across different sectors, collaboration within the approach. I've just highlighted two specific things. If you are an early career researcher and you're looking for some advice, the QR code here gives you an indication on the mentoring scheme that TIES has developed. And we also have webinars, monthly online, October to May. And the reason for picking out these two things in particular is that they're open to everybody. So you don't need to be a member in order to be on the mentoring scheme or join the webinars. We would hope you might be in a position to join, of course, but initially anybody can be involved in these. And the final thing I was just going to highlight pulls that all together. There is a session directly after this today, well, after you've had coffee, that is, at 11:30, and that is all about helping statisticians to thrive within environmental, agricultural and biological sectors. So representatives there from all of these different groups. I won't go through all the acronyms now, but just pulling together some of the things I've mentioned, the environmental stats section, ties, etc. Okay, so I'll finish up just with a bit of a summary and then a point towards the future. What I wanted to get across today is that for me, data fusion and integration, but importantly in collaborative teams, can provide a richer picture to hopefully help inform monitoring and management of ecosystems. Environmental monitoring is a very fast-moving landscape, rapid innovation in the potential data streams, and I hope I've highlighted some of that today. But just for a bit of fun, I asked ChatGPT in July what it saw was the latest innovations in environmental monitoring. And you'll see that a lot of that is the type of thing that I've talked about today and that I'll come on to mention in a minute. So there are many evolving areas for further statistical and data analytics research, moving much towards this collaborative systems approach where we need to think about environment, ecology, society together, and different opportunities for you to get involved as well. In terms of our interests for what's next, well, MOT for Rivers and Gallant are very much ongoing. But also over the past couple of years, we've started to talk more about digital twins or digital replicas for water catchments. And the idea there is really thinking about combining environmental statistics, numerical modelling, and AI. There's a lot of work coming out now in foundation models for AI, in particularly for looking at weather prediction and replacing numerical weather prediction. And they are producing what looks to be very accurate predictions. But of course, there's still a lot to be learned there in terms of the interpretation, the uncertainty around it all. So how can we use these different tools and approaches? How can we combine environmental stats, numerical modelling, AI to integrate the types of different diverse data streams I've talked about today and look at improving computational efficiency, but also providing uncertainty metrics appropriately? So this is the type of thing we're interested in moving on with. Various projects still ongoing as well in terms of GWS Stat, SenseH2 and ExaGeo, again, still looking at that environmental monitoring network optimization. How can we work towards always having the best monitoring network, most appropriate monitoring network, and most efficient monitoring network? With that, I'll finish with acknowledgements. A lot of people have funded this work from the research councils, and I think the most important thing probably is my disclaimer at the bottom. As I said earlier, it's very risky to name people because you'll probably miss someone. Apologies if I have. So I acknowledge everybody that I work with. And I'll just finish just with some references to some of the work that I've shown today. Thank you for your attention.
Okay, thank you, Claire. I think we all enjoyed that. We have a few minutes for questions. If anyone has a burning question they'd like to ask from the floor, if you could indicate by raising your hand, and we'll try and find you a microphone. Otherwise, I'll start with a question from the chat. And the question which is currently most popular is, looking at social media posts, do you have a way to get around false posts, such as AI-generated posts or old photos reposted? Oh, great question. Through a lot of work at the moment. That's the only answer. So in terms of what we've done so far, Luigi spent a lot of time screening the posts that we were looking at. It is something that needs a lot more work.
Hallucinations are still something that is an issue, as everyone will know, right across AI, and so I don't have the answer for that at the moment, but it is obviously something that we need to be very careful about, and at the moment takes a lot of work.
Superb, thank you. Are there any questions from the floor here? Shall I just continue with the questions in the app? Fusing data from multiple sources is difficult. Is there scope for designing data collection in such a way to simplify data integration? And that might be, for example, where you might be able to have some input, such as the river network monitoring.
Yes, probably, yes. I guess it comes back to the questions that we're interested in. And at the moment, the fact that we probably actually have too much data. And so it's actually trying to identify what data is useful, what should we integrate together. And of course, it might be in designing new networks that you could do it in such a way where you could absolutely simplify that challenge. But I think at the moment, it's probably more down to the amount of data that's out there. Do we need it all? How do we use it sensibly? And when is it useful to integrate it?
I guess location is important in this thing. I think it was slide 18 you had where you were showing the input. You had a plot, a map showing standard errors or standard deviations, and the errors were very small. I think around the extra points,
yep,
around the sensors. So I guess that's where you could help people answer the right questions.
Yes, absolutely. So you could use that information in order to inform where you might want to put additional sensors in the future. I guess where the automatic sensors might be going as well, though, is that they'll move away from being stationary. There's a lot more in terms of dynamic sensors and sensors being able to move through the water bodies. And so that might be an answer to that as well.
Dynamic sensors should change things. I'm still looking around. I can't see any hands up. I can't see anything, actually, because there's lights shining in my face. You emphasize data in your talk, but we know that the future will not be like the past. How can we deal with this problem?
I'm sorry, Mark, there's a big echo, and all I heard was you emphasize data.
You emphasize data in your talk, but we know that the future will not be like the past. In other words, that the world is changing. So how do we know that the modeling that we've done to date will still apply in future?
Oh, great question. Absolutely. So, yeah, we don't know what will happen in the future, but we can use the data in order to understand where we've got to, in order to understand what's driven us to where we are now. But in terms of looking forward, thinking about actually scenario testing. So looking at where we think things might go, looking at different trends, etc., in order to test scenarios within our modelling and think about what that might show us.
Superb. It is a difficult situation. I'm just looking at the other questions. I'm not sure if I'll ask this one. Is donut economics different from a circular economy?
Oh, I'm going to plead naivety here and defer that one to the experts. I've heard them both mentioned in the same way, but I am not an expert in the area.
Superb. Oh, I won't ask that one either. Is in your lake data fusion example, does the model give equal weight to the point and aerial data sets?
In the example that I showed, yes. But in other developments that we've been looking at, we've been putting in, for example, different levels of uncertainty depending on the product that's been put in.
Excellent stuff. Would there be situations where you might want to vary it? Give more weight to one particular data set than the other?
So definitely in terms of the uncertainties, there's often the situation where one data source is thought to be more accurate than the other. I guess that's something that could then be expanded out from multiple data sources as well. I would need to think more about that. But my instinct would be yes.
It might depend on the particular question, I guess.
Yeah, it's going to come back to as well, just that, the question you're trying to answer, because while a lot of what we're doing, we're hoping we're being representative, that's not necessarily always what you're going to be interested in. You might be interested in preferential and accounting for that. So.
Brilliant, thank you. Okay, I'll ask one final question. Do you have a question over there?
hear me? Yes, thanks. Thank you for the talk. So I just wanted to shortly ask, you mentioned different types of data and also citizen science data that were a topic of one of the meetings in last year. So it's a technical question. How do you combine all of this into the quotient process, warped quotient process framework that you mentioned, all different types of data? Do you use any corrections? And how does this work, in particular, computationally? I would assume this is...
I'm really, really sorry. The acoustics in here are not good. I really didn't hear that. Mark, did you?
No, I'm afraid I couldn't.
Could we maybe talk later? Would that be okay? I'm sorry about that.
Apologies for that not working, but can I ask one last question, which is, what advice would you give to career young statisticians interested in starting research in this area?
Oh, great question. Get involved in some of the different organisations that I've talked about today. Please feel free to come and speak to people like myself, but also really look to work in these larger collaborative teams. For me, one of the most important things about environmental statistics is working with the experts in environmental science. I'm not an environmental scientist, and so we need these collaborative teams.
Fantastic stuff. Thank you, Claire. Okay, apologies, we have run out of time, so I will close the session, but I think if everyone can join me in thanking Claire again for both the seminar and to congratulate her for being final.
Thank you.